Hi guys, Audrey here. So we have officially finished the part of the class that talks about limits and continuity. We understand what the limit is, what it means in terms of like reality versus expectation. We understand what continuity is and the relationship between continuity and limits. We understand what they look like on a graph. So we are now moving into the portion of the class about derivatives. A lot of you have been asking me about derivatives. We're finally here. So in order to start our conversations about derivatives, we actually need to start with a conversation about slope. So in order to start this conversation about slope, we actually have to define two different types of lines. You've probably heard of both of them, but if not, it's not a big deal. We're going to talk about them in depth today. The first type of line that we want to talk about is called a secant line. So a secant line is a line that bisects a curve at two different points. So what that would look like would be something like this. So maybe I have a point right here and a point right here, and if I draw a line that goes through those points, that is a secant line. Or it could look something like this. I have a curve that's more of a parabola, and again, I have two different points on that curve. That line bisects at those two different points. So that is also a secant line. So it just kind of like chops the curve at two given points. So that's my secant line. Now the other type of line that we're going to be talking about today is a tangent line. And a tangent line is a line that touches the curve at just one point, but is also parallel to the curve at that point. So a tangent line to a curve at a given point, x equals a, is a line that touches the curve at that point and is parallel. And is parallel to the curve at that point. So what a tangent line will look like is, instead of having 2 points on my curve, I'm going to have one. And let's say that I have that same like parabola shape that I had over there. So my tangent line, I have that point right there. It's only 1 point, and it's just going to briefly graze the curve at that 1 point, so that whatever the slope is, it's parallel to the curve. So it's just kind of grazing the curve. So another way that we could look at this, if I have a different kind of curve, maybe I have something like this, and I want my tangent line at this point right here, well, that tangent line is going to look more like that. So a thing that's important to understand about these tangent lines and secant lines is, with the secant line, it's that I'm given 2 points and I know that the line bisects the curve at those 2 points. That doesn't mean that it doesn't also touch the curve at another point. It just means that I'm not given that point. So here I have these 2 points. I'm told this line goes through those 2 points. So for example, in that first secant line curve that I drew, if I were to continue drawing that curve down like that, notice the secant line does go through the curve at another point. Not a big deal. I was only given those 2 points right here. And so the tangent line is going to be somewhat similar. It doesn't necessarily not touch the curve at another point. It's just that we're given 1 point. We know that it grazes the curve only at that point and is parallel to it. So in the two curves that I've drawn, we can see that it's very unlikely that the tangent line will actually touch the curve at another point. But if my curve were to do something like this, or like that secant line curve that I drew up there, so instead of just having that parabola shape, maybe I like have it go back down, and I want to draw my tangent line to the point right there, well, that's going to be a line that's parallel to the curve. So it just grazes the curve. It's not going to touch around that point. It's not going to touch anywhere close to that point. It grazes that point and is parallel to the curve. But notice that if I keep drawing that tangent line forever, it is going to go down and touch that curve at another point totally far away. That's not around the point that I'm given. Okay, so we know what a secant line is, and we know what a tangent line is. And that tangent line, so we kind of defined it as it touches the curve at that point and is parallel to the curve at that point. So we're actually going to use a tangent line right now to describe, or to define even, the slope of a curve. What is the slope of a curve? Well, we know slope is rise over run, but we can actually say that the slope of a curve is the same thing as the slope of the tangent line at that point. So if I want to know, well, what is the slope of this thing right here, or actually let's do this in another color, right here, well, the answer is whatever that tangent line is, it's the same slope. They have the same slope. So what is the slope of a curve? Some value, some x value, x equals a. And the answer is it is the same as the slope of the tangent line. It's also important to notice that, like, here I've said, what if I want the slope of the curve right there? Well, if I were to ask you for some other value, like maybe right here at this other point that I'm drawing, so we're at the top left curve, that second point that I'm drawing right here, it's gonna have a different slope. So unlike a line where the slope is constant, that rise over run stays the same for the whole length of the line, the slope of a curve is constantly changing. Unlike a line, which has constant slope, the slope of a curve is constantly changing. Okay, so basically what we're saying is, what is the slope of a curve? Well, the slope of a curve is the same thing as the slope of a tangent line. They know that the slope of the tangent line is constant, even if the slope of the curve is changing. So it's the slope of the tangent line at a specific point. So if I want to calculate the slope of a curve, it's enough to find the slope of the tangent line. To calculate the slope of a curve, it is enough to find the slope of a tangent line. But how many points do I need to calculate the slope of a line? Hopefully in your heads, or even out loud, you're saying 2. Exactly, I need 2 points to calculate the slope of a line. And with my tangent line, I only have 1 point. So the new question is, how can I calculate the slope of the tangent line at a point when I only have 1 point? So that's the question that we're going to try to answer right now. How can I calculate the slope of the tangent line when I only have 1 point? Question mark. That's question mark in case you were wondering. So again, I remind you, we need 2 points to calculate the slope of a line. This is our big question of the day. And this is where that new idea of secant lines comes in. So first, let's remind ourselves of what the slope of a line is. The slope of a line is y2 minus y1 over x2 minus x1. Okay, so let's draw a curve here. I'm going to have just like a parabola because usually those are the easiest to deal with. And let's say that my goal is, we know, to find the slope of the tangent line. So that my goal is maybe to find the slope of the tangent line at this value, which I'm going to call x is equal to a. So this is my goal to find the slope of this tangent line. And in order to figure this out, I'm going to start off by first drawing a secant line. So I'm going to go over here and I'm going to define some other point. And I'm going to draw a line through those 2 points. So this is my secant line, right? Well, what I'm going to do is I'm going to say that I just picked some random point that's to the right of A. So I'm going to call this A plus H, where H is some number. I'm just saying it's some number that causes that other point to be somewhere on the right side of my A. So in other words, I'm just adding some value to A. If A was 2, then maybe that point is 3, maybe that point is 4. We're just adding something to A to make it not A, to make it further away from A. So in other words, we're defining some other point on the line with x equals a plus h, where we're just adding some small value to the x value. Now, if this curve is called f of x, if I let my curve be f of x, we can use that to now find the slope of this secant line, because now I have 2 points. So let's think about what those 2 points are. This first point, my x value is a, which would make my y value be f of a. At this second point that I've defined here, my x value is a plus h, which would make my y value f of a plus h. So the slope of the secant line, is equal to the change in y. So change in y over the change in x, which in this case is equal to f of a plus h minus f of a divided by, so that's my change in my y values, then my x value is a plus h minus a. So in other words, this becomes f of a plus h minus f of a divided by h. Okay, so this is a little abstract because we don't have actual numbers here. We're kind of defining this as like our x value is a, our other x value is a plus h. So take a second and make sure you understand where that slope came from. If you have questions, you can send me an MIO or ask me on Teams. What does this mean? So take a second and think about that. Okay, so thought about it. We have our secant line. We have the slope of our secant line, and we still have this tangent line for which we don't know the slope. So the question is, how is this useful for us? How is this going to help us find the slope of the tangent line? And the answer is, I want you to think about what would happen if I let this point right here, my second point for my secant line, what would happen if I let that point get closer and closer to the point on the tangent line? So what would happen to the slope of the secant line if I let the second point get closer and closer to the first point. And the answer is, I'm going to show you. I'm really terrible at drawing, so I'm not going to draw it. We're going to go and we're going to look at a little animation. Okay, so we have our function f of x. We have our secant line that's going through points A and B. So that's our blue line that we have right there. Our first point is A. Our second point is B, that we said our x value was A plus h. And then we said the slope of that secant line is f of A plus h minus f of A, all divided by h. And the question was, what is going to happen to the slope of that secant line if I let my second point, B, A plus h, get closer and closer and closer to that first point? So what's going to happen? Well, why don't we look at this? So right now I have that slope, it kind of looks like that. If I let B get closer and closer and closer to A, notice what's happening. Slowly that slope is turning and becoming in the same direction as A. And as it gets super close, notice the slopes are quite close. And if I let B get closer and closer and closer and closer and closer, well, what's happening to the slope? You'll notice that the slope of the secant line is getting closer and closer and closer to the slope of the tangent line. The slope of the secant line is getting closer and closer to the slope of the tangent line. And in fact, if I let it keep getting closer and closer and closer, when it gets to A, when that point arrives at A, what would we expect the slope of the line to become? So when the point arrives at x equals A, what would we expect the slope of the line to become? And the answer is, let's watch that one more time. I'm way over here. Notice that slope has nothing to do with the slope of the tangent line. Actually, I can even make it so that it's perpendicular. There we go. And now I'm going to let that second point get closer and closer and closer. So now it's back at that A plus h that I originally defined. And I'm going to let it get closer and closer and closer and closer and closer and closer. And suddenly now they both have negative slopes and get closer and closer and closer. And that slope of the blue line is getting closer and closer to the slope of the green line. And then when I get to A, well, it looks like if I actually stay on A, it gets there, so that they have the same slope. In other words, we would expect, and that expect is an important word, we would expect for the slope of the secant line to become the slope of the tangent line. So the answer is the slope of the tangent line. Okay, so let's think about another thing. What's happening to my second value, to my B value, as I let it get closer and closer and closer? So if I start here at A plus h, what I'm doing is I'm letting that A plus h get closer and closer to A. So as I'm doing that, what's happening is that h is getting smaller and smaller and smaller. So maybe I started off with 2 plus 1, and then I'm saying, well, actually, let's get closer and closer to 2. So then I'm like 2 plus 0.5, 2 plus 0.4, 2 plus 0.3. That h is getting smaller and smaller and smaller. In fact, we could say that h is getting closer and closer to 0. So we have, as h is getting closer and closer to 0, we would expect the slope of the secant line to become the slope of the tangent line. Think about that for a second. Okay, I'm going to say it one more time. as h approaches 0, a plus h gets closer and closer to a, and we would expect the slope of the secant line to become the slope of the tangent line. But what do we use to talk about expectations that we've been talking about the whole semester? Limits. So in other words, if our limit is our expectation. Right now, our expectation is that that slope is going to become the slope of the tangent line. So what I have here is that the limit as h approaches 0 of the slope of the secant line, which we said was f of a plus h minus f of a over h. So that's the slope of the secant line. Should be equal to the slope of the tangent line at x equals a. But we have said that the slope of the curve is defined to be the slope of that tangent line. So the slope of the tangent line is also the slope of the curve at x equals a. So suddenly we have this limit that allows us to find the slope of those tangent lines. So if we go back and look at the picture I've drawn, I was able to find the slope of that galaxy line. But now looking at the limit as h approaches 0 of that slope of the secant line should result in the slope of the tangent line, which is actually really, really awesome because I know how to calculate limits, and so do you. So that said, this thing right here is called the derivative of the function. In other words, the derivative is the slope of the curve, is the slope of the tangent line, is a limit. So that said, let's let that sink in for a second. That said, that a right here was arbitrary. I just picked it to be whatever I wanted. Right? Like that a could have been 2, it could have been 7, it could have been 6. In other words, it's a variable. It doesn't matter what it is. I can put any value in there. So this, we said another word for this is derivative. Is my derivative of f of x at some random value x is equal to a. But a could be anything. So let's take a minute and actually define now the derivative of the function. So the derivative of a function f of x. First of all, we need to talk notation. So denoted by f prime of x or dy dx. So we have two different notations for the derivative that they can be used interchangeably. The second one, that dy dx, really stresses the fact that this is a slope. That's like change in y over change in x. So what this is it's that limit that we just looked at is defined to be f prime of x is equal to the limit as h approaches 0. Instead of a, we said a can be anything. It is therefore variable. It can therefore be replaced with a variable f of x plus h minus f of x divided by h. And it represents the slope of the curve slash the slope of the tangent line for any given value x. Any given value And this definition is super, super, super important. You need to memorize it. Regularly, you are asked to give, for example, the limit definition of the derivative. That's this. You need to know this. You need to be able to state it. So this is the limit definition of the derivative. And now that we have it, I'm just going to go back and look at that graphic one more time so that we can make sure that it's really in our heads. And then in the next video, I'm going to do some examples where we use this. Okay, so we have a different function now just so that we can see this a little bit differently. So we have f prime of x. That's the derivative of x. So that little dash that we put up there, that's one of the notations that we use. And we read it f prime of x. So our derivative of f is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And what that's telling me, so here I've defined my a instead of being a to just be x. And we have some value on the right that's x plus h. And we're saying as I let x plus h go to x, that's the same thing as letting h approach 0. So as I do that, notice here, I'm letting that second value get closer and closer and closer. Look, those tangent lines get really close really fast. So by the time that I get up to a, check it out, those tangent lines are the same thing. So when b gets to a, when x plus h becomes x, we expect for the slope of the tangent line and thus the slope of the curve to be the same as the slope of the secant line. So those secant lines are approaching the slope of the tangent line. They're getting closer and closer and closer to it. And now this is important to understand. The derivative is a function because here that a was defined right there, but it really doesn't matter. Like I can define a to be wherever I want. If I define that to be a, well, suddenly I've picked a new a value, I have a different x, I can let b get closer and closer and closer. Notice those tangent lines, or the secant line is nothing like the tangent line, but then as it starts getting close, it gets closer and closer and closer, and we would expect by the time it gets to a for guess what, those set lines to have the same slope. So this is our derivative, and in the next video, we'll do a couple examples to try to understand this a little more concretely.